Okay, so hello everyone. Today I'm going to discuss about the BJT Common Base configuration. So this is the symbol of a BJT, NPN BJT, and over here, basically in all the BJT configurations, we will try to bias it in the active region. So in case of common base configuration, the input is applied between the base and the emitter terminal, and output is taken from the collector and the base terminal. So here, in order to bias the BJT in the forward active region, we have to forward bias the base emitter junction. So to forward bias base emitter junction, we connect external supply VEE in this manner, and collector base junction has to be reverse bias. So the supply voltage VCC is biased or connected in this manner, as you see on your screen. All right, and the various currents flowing in the circuit is our terminal currents are IE, IC, and IB. So we have voltages VBE and VCB to monitor throughout. All right. So for a BJT to use as an amplifier, why do we bias it in the forward active region? Is because is the region where it's more preferred for BJT to be acting as an amplifier. So for that we have to keep the base emitter junction forward bias and base collector junction reverse bias. Okay, and this is the structural view of the same thing, right? We have drawn the NPN structure. This will be used when we explain the working of it in different details. So the various terminal currents in the BJT will be IE will be equal to IC plus IB. So also one step ahead, the behavior of the BJT in the common base mode can be described by two characteristics, that is input and output characteristics. And also why the name common base is because base terminal is common between the input side and the output side. That's why the name common base configuration. Alright, so now let's proceed forward and discuss about the input characteristics. Alright. Okay. So over here the input current is IE and the input voltage is VBE, as you can see over here. So input characteristics is between VBE and IE at a fixed value of output parameter, which is VCB. Okay. So here on the left hand side you see the input characteristics. Yeah, let me adjust the screen. Yeah. Yeah, so here we have the input characteristics of for the common base configuration, and one thing you can notice is it's similar to your forward characteristics of PN junction diode. The reason being is your between the base and the emitter we see there is a p and n layer, right? It's acting as a similar to your PN junction diode. So as we go on increasing the value of VBE, we are forward biasing the base emitter junction, so your current will IE will flow exponentially, with respect to increase in VB voltage because of diffusion process. So in this case, the more of the emitter is emitting the electrons into the base terminal, and hence with a constant VBC voltage, that means your base collector junction is reverse bias. So with that constant and only your VB increasing, more and more now carriers are pushed into the base, and then they are reaching the collector terminal because of the reverse bias electric field between the base and the collector junction. So therefore as you increase the value of VBE voltage, your IE voltage increases exponentially. Okay. Now the second question is, we see the two plots over here, one for VCB equal to 10 and one for VCB equal to 5 volt. So what will happen is that as your VCB is increasing, the curve is shifting to the left hand side. Okay, as you can see, the red curve is onto the right and the left curve is on, the blue color one for 10 volt is to the left. So curve is shifting to the left hand side. Why? So we'll analyze this why it happens right now. So here it is, as you can see very clearly, as for the same value of VBE, the curve, the IE value is increasing. IE value is increasing for different values of VCB constant. Okay, so we'll try to address this question now. Ki why as you increase the value of VCB, the curve shifts to the left hand side and I increases also slightly. So let's try to understand it with the help of this structure. Okay, so what happens is as you increase the value of just a second. Yeah. So as you increase the value of the base collector junction, I mean the voltage VCB, as you increase the value of VCB with the help of VCC, your collector base junction become more reverse bias. So if it becomes more reverse bias, the depletion region will increase. The common, let me add it and draw it and show it to you. This is the depletion region, right? So this depletion region width between the base and the collector will go on increasing. So the less voltage is required. So in this case, if this is increasing, less voltage will be required to forward bias the base emitter junction. Okay. So why less voltage will be required? Because the field will become more powerful. Electric field will become more powerful between the base and the collector. So whatever electrons are coming from the emitter region will be drifted towards the collector region more rapidly. So that's why as you increase the collector base, the VCB value, your junction becomes more reverse bias, the width becomes more, and indirectly lesser voltage of VBE will be required to forward bias the base emitter junction. So therefore the curve shifts to the left hand side for the same value of VBE as it is shown over here. Okay, and also the curve shifts to the left hand side for the same value of EBE, and also the value of IE increases slightly because now the electric field is so powerful that it will drive the carriers more easily towards the collector terminal. Okay, so that's the reason why the curve shifts towards the left hand side. Now from the input characteristics, this is my input characteristics, right? So from the input characteristics we can find an important parameter called as input impedance. So input impedance can be determined with by calculating the slope of this curve. So it's an exponential curve, the sum part of it will be a straight line. So from here we can determine what is the x coordinate and the y coordinate. X coordinate we call it delta VB, y coordinate as delta IE. So RAB will be delta VB upon delta IE. So as you can see very clearly, delta VB changes are very small and delta I changes are very large. Alright. So small changes divided by large changes will lead to a smaller value. So your input impedance of the device in the common base configuration mode for the NP and BJT, it's very low. It's in few ohms. Alright. So this is about the input characteristics of the BJT. Now let's talk about the output characteristics of BJT. All right. So this is my on the left hand side of your screen. You see the output characteristics. Okay. And on the right hand side we can see the configuration. So here the IC is the output current and VCB is the output voltage at a constant input parameter which is IE. So we keep the emitter current constant and we plot the graph of IC versus VCB. All right. So if you see this graph carefully, let me expand this graph over here on this side. Okay, so it contains a family of curves. You have plotted the value of VCB versus IC for different values of IE. So first curve is behaving for I equal to 0. Second curve is corresponding to I equal to 1 milliampere. So for increase in the value of IE, the level of IC also goes on increasing, and on this side it's ending at a negative side, that is a -1 value over here. So there are three operating regions over here. The green color one where IE is equal to 0, it's corresponding to cutoff region. The yellow color one is corresponding to the saturation region, and the whole blue color line which we see over here, which we mark 2, is the active region. So now we have to analyze the behavior of this BJT in the common base mode in these three operating regions. So let us start our discussion over here now. So I'll keep the screen on this side and let me bring back this one now so that I can explain you the operation At the same time, yeah, all right. So let the screen be over here. Now, okay. So in the active region, as you can see, the region number 2 marked over here, the current IC remains constant. Now, why it is constant? Because VBE is constant. Now, why VBE is constant? Because we have to keep IE constant. All right, and we know the relation between the value of IC and IE. As you can see on the left hand side of the screen, even if your VCB increases, since we are plotting IC and for different values of IE, the value of IC and IE are very closely related. They are related with a factor of alpha, and they are almost constant. Okay, the alpha is almost less than 1 and they are almost constant. Over here, IE is the input current, IC is the output current. So uh, output upon input current will give you the current gain in the common base mode. So this alpha is almost equal to 1 but less than 1. Okay, so here if you increase the value of VCB, there is hardly any change in the the current IC remains almost constant. Okay, with constant value of IE, the current IC becomes almost constant even if you increase the value of VCB. That means even if you make collector based junction more and more, let me show you this diagram. I'll go over here, let me rub it out what we have done before. Okay, so that means what? For a constant value of VBE, we are not increasing VBE. So a fixed number of carriers are reaching the collector. And now if we are going on increasing the value of VBC, there won't be much change in the value of the emitter current. Okay, the collector current will almost remain the same. All right. And why is that? Because the collector current and emitter current are related by IC is equal to alpha times IE, and alpha is almost equal to 1. All right. So let us proceed with the next part of our analysis. Yeah. So one more thing is there that in this region of operation, let me save this file because I'm making some changes. Okay, so also in the active mode of operation, the BJT act as a constant current source. That means for a wide range of voltage change, the current remains almost constant. Okay, so region due to this region is used for amplification purposes. All right, so this is all about the active region. Now what we determine in summary is that with increase in value of IE, the collector current also increases, and and the collector current is almost constant for a wide variety of VCB voltages. Now, let us come to the cutoff region, which is the green color portion over here, below IE equal to 0 milliamperes. So, in the cutoff region, as we know, both the base emitter and the base collector junctions are reverse bias. So, I equal to 0 means what? VE is 0. Okay, your value of VEE is 0, so we are not applying any VB voltage now. It's shut off, right? The emitter is, let's say, as good as open circuit. So there are no carriers flowing out of the emitter region, right? So I also, IC remains almost at 0 milliamperes. Okay, because IE is 0, right? Why IE is 0? Because VE we are not applying, so IE will be 0 and IC will be approximately equal to 0. It's not exactly 0. IC still exists due to the minority carriers because we have made the emitter open, right? There is no VE applied, but there is VCB applied still. So VCB is reverse biasing the base collector junction, right? So there will be some reverse current flowing, and that reverse current we call it as ICBO. That's a reverse saturation current with emitter open. Okay, so what is the relation between IC and IE? So IC is not only equal to alpha times IE plus it is ICBO, when ICBO is the leakage current or the reverse saturation current, which is normally nanoamperes. So that's why you see over here in the graph, this green region is having some existence. Okay, so where I is equal to 0 milliampere, IC is not equal to 0, it's equal to ICBO, where ICBO is the leakage current and its value is in roughly in the range of microampere to nanoamperes. All right. So this is what happens. Nothing much happens in the cutoff region. The device is off, and only leakage current flows into the device. Now let us see what happens in the saturation region. That is the yellow color region of operation. Okay, so over here in the saturation region, as we increase the value of, see, the x-axis is VCB. So as we reduce the value of VCB, what are we doing? We are making it lesser and lesser reverse bias. So here what do you see? The IC starts drastically to reduce. So I see it's drastically reducing and it's going to zero. So let's understand now how why it happens from this diagram. Okay. So what are we doing? We are making VCB lesser and lesser reverse bias. That means we are reducing the value. So the electric field becomes much weaker, and more number of electrons which were coming out of the emitter and going into the collector are now not going fully to the collector region because the voltage is reducing. So as the reverse bias between the as the reverse bias between the base and the collector is gradually removed, the electrons which have entered into the base from the emitter will not be able to cross the collector now. So therefore, I mean, it will keep on reducing. The number of electrons which are reaching the collector will keep on reducing with the reduce in the VCB voltage. So therefore, your IC value reduces, and at one point of time, your base collector junction is reduced such that it becomes forward bias. So now you see it's becoming forward bias, so it will not allow any current to flow, not allow any electron to go from reaching at the collector terminal. So now what happens is both base emitter and base collector junctions are behaving as a forward bias region. Therefore, the current, as you go on in reducing the value of VCB, that means VCB is becoming lesser and lesser positive. I mean, lesser and lesser reverse bias. As you can see from the characteristics, the IC value drastically reduces towards a very low value and finally towards zero. Okay, so this is how the configuration behaves like. Okay, so now I will explain you the last one, that is, so we have covered around, how does the configuration, how does this characteristics, output characteristics is divided into three regions of operation, that is saturation, active and cutoff, and we have seen the behavior, why it is so. And now we will determine the output characteristics, output resistance. So output resistance is the slope of this curve, so it's almost a straight line. So it's a very wide variation. So it will be like x coordinate upon y coordinate. So delta VCB upon delta IC at a constant IC value. This will be pretty high for the common base configuration because delta VCB is a large variation and delta IC is a smaller variation in milliampere. So R out will be very high for common base configuration. All right. Now let us observe the last one over here. Yeah. How is signal getting amplified in a common base configuration? Let us try to understand it. So we have drawn a PNP transistor configuration. Remember a PNP transistor. We can draw NPN or a PNP. So let's consider a PNP configuration over here. So here we have biased this BJT with VBB applied, base emitter junction as forward bias and base collector junction as reverse bias. Okay, reverse bias or zero bias should not be forward bias. All right. So here we call input current as I in, output current as I out. Here we have connected a resistor at the output RL 1 kilo ohm, and we have superimposed AC signal, that is 5 millivolt AC signal. This is just a hypothesis to explain you how does the signal gets amplified in common base configuration. So as we know, we have just now witnessed that the input impedance of a common in a common base configuration is quite low, say around 10 ohms. So what will be my input current? I know input voltage. So input current will be input voltage upon input resistance, that will be 5 millivolt upon 10, that will be 0.5 milliamperes. And we know that the output resistance is pretty high, all right, and your IC current is almost equal to IE. It's related by this factor. IC is all equal to alpha times I. Let's assume that alpha is equal to 1. So we can say that I in is around zero point 0.5 milliampere. So I out is also around zero point 0.5 milliampere because they are related by alpha. And V out is what? V out, you take it from this collector terminal. So V out is I out into RL. So that will be around zero point 0.5 milliampere into 1 kilo ohm. That will be around zero point 0.5 volt. So as you can see, input was around 5 millivolt and output is around 500 millivolt. So if you divide that V out by V in, you will get around gain of 100. So from here we can say that your input signal has got amplified by a factor of 100. So typically the gain can be from 50 to 300 also. Also, the current gain in this configuration is given by, we have discussed before, alpha, which is IC upon I, which is almost equal to 1, okay, probably less than 1. So the common base configuration provides you a very good voltage gain, but a very poor current gain, alright. A very low input impedance, but a very high output impedance. So these are the properties of a BJT operating under a common base configuration. All right. So yeah, that's it for this session. Thank you.